little bit about our afternoon activities. So we'll have a discussion session at 3:45 today, just over here. We have a great set of panelists. And you see this QR code over here. So you can use this QR code to upload questions on Slido, which is this interactive platform we'll be using. So you can upload questions there and also upvote questions that you would like to be raised during the session. So hopefully it'll be a good time to have an informal discussion. Any questions about that? Okay. With that, we can get started with our first talk. Aditi, do you want to switch your slides as well? Oh, yes. So it's a great pleasure to have Aditi Raghunathan here to give our first talk. Aditi is an assistant professor at CMU. She's done really impactful work on robust and reliable machine learning, and actually had the great pleasure of being PhD students together with Aditi. And I've always enjoyed reading her papers and learning more from her about how we can use theoretical tools and the principal methodology to both understand machine learning models and make them better and more robust. So let's welcome her with a big round of applause.
Hey. Okay, thanks, Vatsal, and thanks for inviting me. And yeah, today I wanted to talk a little bit about challenges in building safe and robust LLMs. And maybe it takes a little bit of a different flavor from all the other talks in that it's slightly pessimistic and of showing all the things that are hard to do right now. And feel free to interrupt me. A lot of it is kind of high level and intuitive, and also try to deliberately have some controversial or hot takes just to get some discussion. Okay, so like zooming out of all the details that we've been, which are very important, and we've talked a lot about in the previous tutorial talks, one way to think about what's going on today is we've discovered that pre-training on enormous amounts of data can be really powerful and leads to these models doing very interesting things. But at the same time, we still can't use these models when they're pre-trained directly. We kind of need to steer them in some way, make them usable, make them safe, and so on. And the way our current methodologies try to do this is by doing some kind of fine-tuning. And I think Danchi's talk covered all the various aspects of different instruction tuning data sets, different objectives. And you can see there's a lot of effort that goes into actually trying to steer and make this pre-trained model that digests so much data into something that's actually usable as conversational agents in a safe way and so on. And one of the challenges of doing something like this is that most of this second part, that is the fine-tuning, where you're trying to steer these models, that happens on much more limited data because it requires careful curation. You need to think about what are the safe aspects or what are the task-specific annotations that you need to do. And so fundamentally, you're limited in sort of how much you can scale the second process of actually trying to steer and make these pre-trained models usable. So that's kind of the very high-level takeaway is we're going to look at various aspects of how this process is challenging, and I'll introduce some ideas on what we've looked at and what people could try to do to do better on trying to do safety fine-tuning. So I'll talk about two different aspects. The first is distribution shifts. And we'll talk a little bit about concrete examples of failures that arise when we try to do this kind of fine-tuning for safety on limited data. And I'll talk a little bit about why we should hope to do better and some avenues for approaches for being robust to distribution shifts. Then I'll also talk about adversaries, which are, again, very important to think about when it comes to safety and using these models in the wild. And again, we'll talk a little bit about concrete examples of failures and what people have found are challenging with these, with dealing with adversaries. And maybe going to be a little bit of a pessimistic take that the way we are thinking about some of these safety questions against adversaries might be too difficult to actually achieve. And we probably need to rethink what exactly is the right question to ask, or what is the right scope of adversarial safety one must try to get. And I think that is the big open question when we think about adversaries interacting with these models. Okay, so that's kind of the overall story. And with that, I'm going to talk a little bit about distribution shifts that arise and kind of why safety fine-tuning is brittle to these distribution shifts. Okay, So this is just like a pictorial visualization of what we can think might be happening. Is we have this really enormous pre-trained model that's been trained a lot of data and has some way of digesting all this information, and then we are trying to steer it in some way, and we might do that on limited data. And the question is, what happens outside this narrow scope of fine-tuning data that you used? Has this process actually generalized in a way that we expect it to? So I think Tengu touched upon this a little bit, but just to gain some intuition, like here is one example. And so we take a pre-trained model. So this is a model that has just been trained on a lot of data in this autoregressive format. So there's no instruction tuning, no safety tuning. It's not steered in any way. And Tengu spoke about in-context learning. So just to recap, like that's when you try to give a bunch of input and output examples to the model, and that helps the model infer what is the task. And so we can ask kind of, if you give an input like this, where there is an instruction, and there's also examples that the model can see to figure out what the task is, and then you give an input something like this, let's try to guess kind of what the pre-trained model is going to output. So how many people here think the model is going to repeat what is 2 plus 2 rather than answering 4? Okay, a few hands. Okay. And so we're not debating what's the right answer. We're just trying to understand how these models behave. So if you take a pre-trained model, they are good at so-called in-context learning. And so they do pick up this pattern here, and they're going to say what is 2 plus 2. Okay, so this is on Llama 2 models. I think that later ones, they have even their pre-trained models are post-trained in some ways, so we're not going to look too much into that. But the pre-trained Llama 2, this is what kind of happens. Now, when you instruction tune these models, so like, for example, like I guess Tatsu's here, like, Alpaca from his lab, or other models that people have fine-tuned Llama 2, the base model, to make it better at following instructions and conversing with people. Okay, so with this model, like, how many people think the model is still going to say what is 2 plus 2? Few hands. Okay, so it turns out that this model actually says 4, and I think Tengu alluded to this a little bit, that with like he was finding it hard to get models to do in-context learning, the recent models, because they have been really tuned to follow instructions. So this is one example to kind of distill that it feels like maybe the model has forgotten its ability to actually do in-context learning and tends to just follow instructions, which may not be a good or bad thing, but it's just about like what it seems like these models are doing. And this kind of gives hope that we could stop models from outputting dangerous things by doing similar fine-tuning. So this is on GPT 3.5, and even the later models, all of them, if you ask a question, something like this, they're going to say, sorry, I cannot help you write a script. This is harmful. And things look like, yeah, it's probably learned that something is harmful and it shouldn't do it. And just like the previous slide, we can think about, has the model in this process of fine-tuning forgotten its ability to write spam emails? And to dive into this a little bit, I guess the short teaser is the answer is no, and we kind of wanted to think about it a little bit with simple tasks that we could actually play around with and look at. And for people who are here on Roger's talk, like he spoke about all these different personas that language models can have. And so one way to make this concrete is, let's just take a model that can implement 2 different algorithms. It could do either ridge regression or it could do discrete regression. And during pre-training, we want the model to do both these algorithms to solve both these tasks. And then we can ask what happens when we fine-tune it to exclusively do one task versus the other. Like, does that actually help the model completely forget the previous task? Because that's kind of the overall scheme that people currently use for safety training, where you only fine-tune the model to do safe tasks. And so does that mean the model cannot do these unsafe tasks? And we don't have to go into the details, but for people who are here, and I think a lot of talks covered this linear regression setup. And so we can autoregressively train transformers to do either ridge or discrete regression by sampling latent weights and then showing samples to the model. So again, it doesn't depend on the details here, but by changing the distribution of the weights, you can actually get a model to do either the either the ridge regression when it's a Gaussian prior over weights, or if you fix a discrete set of weights, the model is not going to do ridge regression, is instead going to do discrete regression, which is the Bayes optimal thing, where the model figures out which is the most likely weight vector in your discrete set and executes that, like outputs the y corresponding to w times x. So, and just to check that the model can actually execute both these algorithms, I think there's obviously interesting theory questions on why transformers can do that and so on, but we do empirically observe that by changing the distribution of the weight, we can get the transformer to solve both of these tasks. So it can express and solve these tasks. And so, and you have like a continuous distribution over the weights, the Gaussian distribution, the model does do what looks like ridge regression if we look at how the error evolves as you increase the in-context examples. And if we do like a discrete set of weights, it again looks like the model is no longer doing ridge regression. It's actually doing the Bayes optimal discrete regression. And I think Surya's talk also covered about how with few discrete weights, the model doesn't actually generalize to other weights and doesn't do ridge regression. Yeah.
Thank you so much. Sorry, just to clarify, is this with an LLM? Like, are you asking an LLM?
No, this is training a transformer from scratch.
Okay.
So the transformer so we are precisely controlling what are the tasks the transformer knows how to do. Okay, any other questions? Okay. So now we kind of can pre-train on a distribution of these tasks and then fine-tune on one of these two tasks and see what happens. And so we do the same thing. We pre-train on this mixture, and then we fine-tune on just the discrete regression. Okay, so what we see, so we can plot the loss on the discrete distribution. So you see that the model actually kind of slowly drops in this loss as we pre-train the model on this mixture. And if we fine-tune on only the discrete distribution, the drop is even faster. And you see this like kind of like a big jump immediately when you start doing fine-tuning here with the loss. So the model gets really good at modeling or doing this discrete task when we fine-tune. And we see a corresponding, like a big jump in the continuous loss here, where it looks like once you started fine-tuning on this discrete distribution, the model completely lost its ability to do linear regression on like the other weights. So when weights that are not from exactly the discrete set, the model should have still been able to do ridge regression and achieve good loss, but instead, because we're fine-tuned, the model kind of immediately, you can see that the loss immediately jumps. Okay. Any questions about this so far? So this is not that, like, I guess the magical part here is like how quickly this loss goes out. So in both cases, the model it does really well on whatever you've trained it to do, but you can see that the model initially could do this continuous task or the ridge regression, but kind of abruptly looks like the model lost its ability to do that. Yes?
The fact that the loss is going down and going up very rapidly necessarily an indication that the model has completely forgotten how to do perhaps the other how to do the other sort of regression.
Yeah, it's almost like the reverse actually. The fact that it kind of increases so much says that there's like a simpler thing that's going on and the model hasn't really forgotten or like unlearned an algorithm in like a meaningful way. So it's kind of the reverse. So the fact that the loss kind of abruptly goes up says that there's a simpler explanation for what's going on, and I'm going to get to that in a bit. What do you mean? Sorry. Oh yeah, it's not brittle to any of these at all. Like as long as you're able to it has to be big enough that you can kind of fit both of those distributions. But other than that, it doesn't matter. Yeah. And it also kind of, for any alpha, you see something similar. Like, yeah. And if you train long enough, I guess one can ask, like, is this inherent or can the model actually do both algorithms? So if you train long enough, like with any distribution, it'll eventually get low loss. So the model can do both simultaneously. It can express that, but it's just that when we do this fine tuning, we see this particular behavior. Yeah.
Goes down sharply again?
Yeah, you'll see something similar. Yes, yes.
Maybe this is exactly what I talk about, but you attributed this to the discrete being simpler. But okay. So
No, there's nothing about discrete being simpler or harder. So both of, if anything, the discrete is a bit harder because the model, like you can see here, the model learns linear regression quickly. Yeah. Okay, great. Yeah. In fact, we see the reverse, and that's like, yeah, that's yeah. Okay, cool. Okay. So a hypothesis here, which I think a lot of people were kind of getting at various questions in the previous tutorials, is one way to think about what's happening is that, like, this is only when there are two tasks. You can think of every time you give a prompt to the model has to first decide which of those two tasks and then execute the corresponding task. And it doesn't have to be a hard decision. It can be like a weighted probability of each task. And this is exactly like the Bayes optimal way of doing this. So we can think of the model having to do some kind of inference based on the prompt that you give over what task you want to solve, and then there's some kind of capability of actually executing or solving that task. And like one hypothesis is that when we do this fine-tuning, we are actually not probably changing the capability inherent to the model, but we're just changing the inference or the prior of the model as like which of those tasks are you talking about. So the fact that you see the sharp increase kind of suggests that the model doesn't like inherently lose its ability to do linear regression, but it just like it's going to upweight the circuit or the algorithm that actually computes the discrete task instead. So like that's kind of seeing the sudden jump. It says that like the model probably didn't forget how to do linear regression. It just decides to always do the discrete regression or upweight the discrete regression. Yes.
Sorry. So do the P1 P hat correspond to what the model like decides?
Yeah. So I'm not claiming that we can't prove that this is what models do, but the behavior looks like this. Okay. Yeah. Okay, so kind of with that hat on, if all that's going on is when we fine-tune on the discrete distribution, if we believe that what's happening is that this probability goes up so much that the model doesn't, like it still can do ridge regression, it's just that this solution doesn't show up, and the model looks like it's forgotten ridge regression. So if we believe that that's what's going on, where the fine-tuning really increases this the probability of the discrete task, then we can try to do an ablation where let's change the prompt so that we can artificially downweight that probability and see whether we're able to kind of counter this fine-tuning effect. So we can try to generate a new prompt that looks so far from the discrete tasks that the model is not going to think it's a discrete task, and we'll see whether that allows the model to like show its ridge regression abilities. Okay. Any questions? Okay, so the way we do this is, so the way we do this is, so in our current setup, all the weights had a similar norm. And so instead, what we're going to do is we're going to scale the output such that it looks like the weights are actually very different from the discrete set. So this model, the optimal thing for the model to do is still the same linear regression, but it's just that we have changed the output to scale up by some constant lambda. And if we were to get back the answer, we can scale the output down by lambda to get the original solution. So this is a way where we've just we're kind of doing the same task, but we have made the prompt look really different from the discrete set to see whether that can kind of counter the increase in probability that seems to happen with fine-tuning. Right, so the model still has to perform ridge regression, but the weights look very different from the discrete weights, and we're going to see whether this helps. And we see that this actually kind of helps. So here, if you look at the fine-tuned model compared to ridge regression on these like weights that are outside the discrete set, if it did ridge regression, it would follow a curve that looks like this orange one here. But the fine-tuned model seems to have forgotten its ability and like does worse. But when we kind of scale the labels, it gets a little bit closer to ridge regression. So this says that the model probably hasn't like lost its ability inherently to do ridge regression. It's just that on these weights, the model is instead executing the discrete regression because the fine-tuning process really upweighted the prior on it being a discrete task. So scaling, where we have not changed the task in any way, but we're just changing the prompt to make it look one way or the other, bridges some of the gap. So at least in this toy setup, we see that ridge regression isn't completely forgotten. And even though it looks like that, when we fine-tune on like the discrete task exclusively, it looks like the model forgot its ability, but we can just prompt it differently, where like we can scale the model, for example, or we tried a bunch of different transformations as well, where we still want to execute the same algorithm, but the prompt just looks different, and the model starts performing ridge regression. Yes.
Might also be another simple question, but like why not just feed it like a typical ridge regression as like problem as like a prompt, for example, to like that would be very different from like a discrete regression sort of prompt.
Yeah, so when you do that, it doesn't work. That's the thing. So when you just feed it exactly like that, it still executes the discrete task. So which is why you might think that the model forgot how to do ridge regression. But if you prompt it even more different from the discrete set, so when you do the fine-tuning, you've kind of really increase this probability that even when you sample something that's not from the discrete set, the model is going to think it's from the discrete set. And so if you kind of counter that by making the weights look really different from the discrete set, the model kind of tries to shows like ridge regression again. Yes.
Does this imply like some level of causal reasoning, or like a causal chain? Like the model first picks which task it's going to do, and then it executes the task in that way.
I don't know if like, okay. So if we were to actually intervene in that only makes sense if you're going to try to intervene in the activations and try to change what the model is doing. That's not what we're doing. So we can't distinguish between the model just doing all of these in parallel versus actually doing something sequentially.
Okay.
Yeah, and so it's not making a claim about the actual mechanism.
Okay.
Yeah. Okay, so one way to think of what's happening here is that the model could execute two different tasks, example here, and the pre-trained model has the ability to do both of these tasks, and it kind of has some implicit inference over which of those tasks it could be. But when you fine-tune the model exclusively on one task, you might have really increased the probability of the model kind of showing outputs that look like that task, and it could make it look like the model kind of is never going to execute this task or this persona. But we see that if you prompt the model to be very different from what you fine-tuned on, then you can get a new prompt that effectively is the same task, but the model is going to now go back to executing kind of the pre-trained ability of executing the first task. So one way to think of this is that this inference, like this increase in inference of one task versus the other, is basically local to whatever fine-tuning data you did. And if you just prompt like far enough, then you get back the ability to do the tasks that the pre-trained model could do. Yes. Yeah, so that's actually the next slide. Yeah. Okay, so kind of we can try to see what this says for more real-world settings. So applying the same prompting strategy, we are basically trying to find a transformation that goes to a new prompt where this new prompt should have low likelihood under the fine-tuning distribution. And that's one way to effectively counter the increased probability of the fine-tuning distribution that happened while we were fine-tuning. So for example, scaling the weights made it less likely to be discrete, and that allowed the continuous regression ability to pop up. And kind of generalizing that principle, what this says is that if we just prompt it with a new prompt, which looks very different from the fine-tuning distribution, then even though it's the same task, the model can now execute it. And so this was the alpaca example from before. So what we found interesting was that when we prompted the model in English, and as a lot of people correctly guessed, the model is going to say 4 because it's getting really good at following instructions. But if we prompted the same thing in a different language, so we translated here, and now we see that the model actually says what is 2 plus 2. So depending on how we prompt the model in which language, the ability, like whether the model does in context learning or whether it follows instructions, actually changes here. Nati looks confused.
Here, maybe similar. I'm just trying to think similar to the fine-tuning was only in English and not in French.
That's exactly what it is.
But then
Yeah.
why do we need to go through that other explanation? It just doesn't kind of know.
Yeah, so I guess like one way, so the question is like, how do we think of what is out of distribution? And like not saying that this gives a very clear explanation of that, but one thing we can think of is that the model just hasn't like forgotten its ability to do certain tasks, and we can extract those answers in different ways. Yes.
If you remove that corner, that square.
This one?
Yeah.
Yes.
Remove that square. It still asks the questions. What is 2 plus 2?
Oh, it's gonna get the right answer. It's gonna say 4. So the model can follow instructions. Yeah, it's
But
just
it was not
yeah.
pre-trained, but it was not, training on in French.
So there is some generalization that happens, but we kind of see this like when there is a conflict, we see that there are some differences. So yeah, like if a model follows instructions primarily in English, it also tends to follow instructions in French to some extent. But when we see this kind of conflict between the pre-trained and fine-tuned behavior, then we actually start seeing differences. Yeah. Yeah.
This is interesting. So, but can you think of the French as like a third probability distribution instead of as like increasing the prior of your first probability distribution?
Yeah, you probably can. Like I think it depends on like how we think these things are represented in the model. Like is the model implicitly solving all these tasks in the same way across different languages, or is it completely different? I think that's a little bit hard to disambiguate, but yeah, which I guess is sort of like Nati's question, like are they just completely different, or is the model kind of reverting one way versus the other? And I think it's hard to disambiguate those two. Yeah. Yes.
So I just want to make an analogy. They're saying when you do the fine tuning, the original language model would start with 1 plus 1 equals 3, and you crack it to 1 plus 1 to 2. But if you translate the question in other languages, still 1 plus 1.
Yes. Yeah. The model might not generalize. Yes. 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 I think the answer, I think it's a bit subtle. So in some cases it does generalize, in some cases it doesn't. And some, like this was like work about a year or two ago. And so they're like the latest models have also been pre-trained on a lot more multilingual data and fine-tuned on like more multilingual data. So like things might be a little different, but it also depends on like how the pre-trained model kind of stores all of this information to some extent. Yeah.
Since you mentioned that one reason why like this might occur just in the English case is because they've been fine-tuned so much to follow instructions. But like, is there then a corresponding like degradation in the ability to follow instructions when in French? Like otherwise, why isn't French just getting all the benefits from none of the drawbacks? Because it's able to follow instructions without being.
Yeah, that's a good question. It's about like kind of where in this trade-off do we get? Like one could argue that like this is the intended behavior, and so like French is not doing the intended thing. Like it depends on like what we actually want the model to do, and like there are different points in the trade-off that different things could satisfy. Like how much do you want it to like behave like the pre-trained model versus the instruction-tuned model?
Gotcha.
Yes.
The first one doesn't have repeating.
Oh, okay. Like I think we had that in the example. Yeah. This was just a figure issue. Yeah. Okay. So yeah. So I guess another way to think about like why it's useful to think of the different tasks is we just know that out of distribution the model is going to fail, but this kind of says that out of distribution the model reverts to its pre-trained behavior effectively, which can be bad when we think about things like jailbreaking. Yeah, so this is an example from before, but now if we ask the same question, so this only works on GPT 3.5, like this has been fixed now. But if you kind of ask the same question about writing a spam email in a different language, the model actually kind of follows the request. And yeah, so there have been a lot of other papers that also find kind of this thing that it's very easy to jailbreak models by just querying them in different languages. And I guess there have been other transformations that one could think of, like I guess here they transform it to like base 64 and query models, and the model is kind of start following the instructions there. There are other OD or other out of distribution issues, like for example, like a recent paper found that refusal training doesn't generalize to the past tense. So if you ask something like, how did people make something dangerous, the model starts giving you that answer. And there have also been some recent efforts on trying to mechanistically try to explain what might be going on. And here they kind of see that very few neurons or weights actually change when we do fine-tuning. And so that tries to get at like there is some very simple change that's happening in these models. Another kind of interesting version of this OOD issue is, so this is a paper on scalable extraction of training data. So what they find is that pre-trained models typically memorize a significant amount of training data. So if you query with like the start of some sentence, they usually memorize and output. They output the exact match the rest of the sentence. But then if you look at these alignment processes that happen that make these chat models, they found that it was actually very hard to extract memorized data. So either they were kind of trained to reject responses about saying, copyright information, but also something about like the chat template makes it harder for the model to actually output memorized content. And so it kind of looked like this is not really a problem. We can't extract training data because the alignment seems to have fixed it. And there's this really interesting attack that I guess they accidentally discovered, where if you prompt, again, this is like the older 3.5 model, if you prompted the model to repeat the word poem forever, it repeats it some number of times, and then it kind of gets so out of distribution from all the fine-tuning that it starts outputting memorized content, or like there's no clear, we don't really understand what happens here, apart from that this alignment seemed to have avoided revealing private information, but that kind of went away if you prompt with something that like looks far enough. And it's like, so only some words do this, not all words, and this is kind of a phenomenon that like I don't think people really understand why that happens. Yes.
Is the out of distribution related in some way to like the context length that's created by having it repeated so many times?
Yeah, it could be. I don't know if they actually controlled for the context length versus the kind of instructions that people were using. I think it's just like having a word repeated so many times was just really different from anything that the model was fine-tuned on. It didn't look like a chat, I guess. Yeah.
I've heard that some of the pre-trained models, people were having issues with it getting into just repeating the same thing over and over when they weren't wanting it to. Do you think that attempting to solve that introduced this jailbreak?
I don't know if, at least in this setup, I don't think they actually did anything to solve that apart from changing their decoding procedure to avoid like having this repetition collapse, or like the collapse to the mode. So I don't think, at least in this example, like that's what led to it. Yeah.
Yeah. So how do you know if this input is OOD? Because I think it may see lots of weird things like that. So how do you measure that?
In the instruction tuning data? So I guess most of the instruction tuning data looks like it's crowdsourced to have people write instructions that they want the model to follow. And so it's like kind of very unlikely that someone wrote something like this in their alignment data.
Do you have any quantitative method to?
Yeah, I think that's a great question. And I think it's really hard to, there doesn't exist anything right now that helps with answering that question precisely.
I just feel this is weird, but not that weird. People will generate more weird things like that.
I guess it's not out of distribution from the pre-training data. Just to be clear, it's out of distribution from the fine-tuning data. So yeah, so it's coming from the fine-tuning because there is like much more carefully curated to follow human-generated instructions or synthetic data that looks like human-generated instructions. Okay, so I guess we touched on stuff a little bit as to like a lot of these issues we can think of it in different ways, like but really the core issue here is that we have some data that we're fine-tuning on, and why should it generalize? Like this has been kind of a problem all through. Like when I started my PhD, I worked a lot on this because that felt like the biggest problem. And like self-driving cars kind of were much more challenging than people anticipated because of issues like, for example, in this 2018 example, there was a pedestrian who was jaywalking, and the model kind of wasn't trained on such pedestrians, only pedestrians at crosswalks. So that was one among other issues. So there are all these issues that, of distribution shifts, and this has been kind of a big problem in machine learning all along. And it's everywhere, a lot of interesting data sets that people created, and it's very hard to like actually get methods that work reliably across all of these things. So in some sense, it's bad news that, well, we don't expect generalization to be out of distribution generalization to ever occur. But I think why we might be able to do better is that we now have a very rich starting point of pre-trained models. So we could even make the kind of generous assumption that the pre-trained model has been trained on like everything that could exist. And so the model has a really rich information and has digested all this data. And so there could be a lot more that we can extract from these models if we just fine-tune the models properly, because we're not starting from nothing. So back in the day when we didn't have these large-scale models, the common issue was that if the model never saw anything that looked like out of distribution, like all hope was lost. But I think now when we have pre-trained models that have seen so much data, we might be able to actually get a lot more from these models if we change the way we fine-tune these models. So we can think about, for different tasks, maybe this answer is different, but there could be ways to fine-tune the models to maximally preserve pre-trained information and kind of achieve better robustness. For example, these models, they do have a sense of all the different languages, so they should be able to generalize that something that's dangerous in one language is also dangerous in another language, and we might be able to get methods that actually do this in a better way than we currently do. And yeah, to that effect, I guess some kind of thoughts about that were you could try to do a better regularization. So I think a lot of the ideas that we currently use to fine-tune models are very heavily inspired by what we developed as heuristics when we were training models from scratch. And that might not even be the optimal thing to do, because the regularization that you need when you're training from scratch might be very different when you're starting with a rich pre-trained model that you don't want to forget a lot of information from.
Like you were saying that you want this, how do you call it, fine-tuning to actually change the behavior of the model in beneficial ways. So if it, I don't see how to reconcile it with saying it should remember everything it knew before. So you're trying to make it forget stuff, aren't you?
Yeah, I guess it's two sides of the same coin. In some cases, you want to forget information, or you can think of that when the model, you're trying to tell the model what is safe, and you want the model to remember that it could translate what is safe or safe content from one language to another. So it shouldn't lose its correspondence between languages that it had from pre-training. That's one way to think of it. So I think it's basically it's almost the same question. You just want more precise control over what of the pre-trained information to forget or not. But in order to do that, we kind of need a sense of what real world distribution shifts are, what are the cases it should naturally work, and that could come from the pre-trained model effectively. Yeah.
Follow-up.
Yes.
Reason about pre-training the data, the model on everything versus only pre-training it on non-harmful content.
Yeah, I think so at least companies right now do try to do some kind of filtering before pre-training as well, but they usually try to filter out some toxic content or personally private information. So one argument that people have is that the model needs to know what is harmful, and for that we need to, and so that it can effectively not be harmful, and so for that you need to train on harmful data as well. Yeah, so yeah. So it's kind of maybe a similar thing. Do we want to rely on the model's ability to generalize the notion of harmlessness and harmfulness? And people feel maybe that's a better thing to do rather than just handicapping the model to never understand what is the notion of harmful or helpful. Yeah. Yes.
So this is interesting. That argument makes sense to me that you have to have seen it to know that you shouldn't do it or
Yeah.
Is there a mechanism to remove that rather than disallow it? So that the general concept is learned, but the actual.
Yeah, I think that's kind of one of the open questions. We don't have ways to try to get at that, and I'll talk a little bit about that. But people try to say that maybe we can erase some activations, or maybe this neuron stores some concept that we can erase. All of those are very imperfect science at this point, so it's really hard to do this in any reliable way, partly because we just have not enough idea for how all these algorithms or abilities emerge in these large scale models, so it's hard to control them. And I think that's there's a lot of scope to actually try to do better there. Okay. So I guess just to give some kind of ideas and proof of concept that you can actually do a lot more here. So this notion of robustness and fine-tuning has been looked at more is like a bit more mature in vision compared to language for various reasons. So I'm going to show a few results related to fine-tuning and robust fine-tuning when using models like CLIP for image tasks. And I think the general ideas or principles apply, though the direct techniques might not. Okay, so here's one example so this is from 2 years ago, but I think this was sort of one of my first results where I actually felt like there's clearly so much better we can do with how we fine-tune models. So if you look at these image pre-trained features, the two kind of common methods that people did to use pre-trained features for their tasks were these two methods. So one is called fine-tuning, or full fine-tuning, which was the more common method, where you introduce a linear head. Like if you're doing classification, 10-class classification, you have like a 10-dimensional linear classifier, and then you usually initialize this head randomly and then propagate gradients all through. Okay, so you're kind of initializing these features with the pre-trained model. And when you have a downstream task, you initialize the pre-trained features, have a randomly initialized classifier on top of that, and you update the features as well, minimizing whatever loss. It could be some cross entropy or whatever, any generic machine learning loss on your downstream data. So usually that was the most common thing to do. Like if you had the ability and memory and compute to actually fine-tune all parameters, that's what you would do. The other alternative was linear probing, where we kept the features fixed. So we didn't update the parameters, but we only learned a linear classifier on top. So this was called linear probing. And usually if you're bottlenecked with compute, you would try to do linear probing and not worry about updating the features. Okay, any questions about these two methods before we try to look at how these methods work? Yeah. You could, yeah. All of the stuff that we talk about next could apply there as well. But the idea is that you want to make your life easy, and the hope is when you do large-scale pre-training, your features are good enough that is linearly separable, so you don't need to do nonlinear probing. And if you had less data, you probably don't want to learn a very complex thing also. Less downstream data. Okay, so the common wisdom is fine-tuning works better than linear probing. So if you could do it, you should do it. And so this is average over 10 data sets, very standard vision data sets, where we see that if we compare linear probing and fine-tuning generally does better than linear probing. And there was no surprises here. If you can update more parameters and fine-tune them, it seemed like strictly a better thing to do. And so the common wisdom was to do fine-tuning rather than linear probing if you could. But putting on this idea that I was saying before, that maybe for robustness, if you actually look at certain distribution shifts from your downstream task, from your data set, for example, sketches or slightly different geographical regions and so on, maybe the story changes there. And what we see is that linear probing actually does better than fine-tuning because you don't change your features, you're preserving your features, and that actually enables the model to generalize better out of distribution compared to fine-tuning. So a lot of the common wisdom was to do full fine-tuning if you could, but that's actually a bad thing if you care about robustness. And I guess when we saw this table, it felt like you should be able to do best of both because there's clearly enough knowledge in the model to be robust. And it can also improve performance. So is there a way we can actually get the best of both? So that was sort of the next question. And in order to answer that, we try to dig in a little bit more into what is it exactly about fine-tuning or linear probing that's causing this difference. So we have a theorem we prove for linear two-layer networks in our paper, but I wanted to just give the intuition here because it's basically very simple. So here is a picture we could draw for in and out of distribution. So let's say we have two distributions in blue and green, and we care about classifying X's and O's. Okay, so let's say the pre-training on large scale was so good that the model was actually able to extract some kind of a relationship between X's and O's that are kind of represented in the feature space like this. So now what happens with conventional fine-tuning methods is that you start with a randomly initialized linear head. And now what happens is when you pass gradients through this linear head and then the features are going to also change to accommodate the linear head and vice versa. So if you actually track the gradient updates, it's going to look something like this. So the features are going to also get updated and the linear head's also going to get updated. And you might end up with something like this, where the X's and O's are separated. In distribution, you have good performance. But in the process, you're actually broken the correspondence between in and out of distribution, because whatever updates you were doing on the features here was only on the in distribution data, because the downstream data was only blue. So if you've only updated on the in distribution data, we need to be careful because the features changed a lot to accommodate the linear head, but it didn't correspondingly change out of distribution, though our pre-trained model had that information. So because of, like, here's an example that basically what happens is whatever classifier we end up actually performs poorly out of distribution, but is okay in distribution because the features were updated. But in linear probing, we kind of freeze the features. And so we get something like this, where we don't break the correspondence that was learned, but then we're also a little bit handicapped that the features might not be perfectly separable, but we haven't been able to like fix that, because we don't allow features to be updated. So it kind of works reasonably, but it's not perfect, but it's better out of distribution. I guess, does this inspire any ideas on how we could kind of get the best of both? So the issue we had here was that we had a randomly initialized linear classifier, and then the features were getting updated to kind of, because when we pass gradients through everything with a randomly initialized linear head, the features are going to change in a way that accommodates your current linear head, and the linear head is going to change to accommodate your current features, and they kind of move in tandem. Yeah. Okay. Okay. So, yeah. So I guess like one thing you could say is that a lot of this issue just was like, I mean, the features changed more than necessary because you started with a randomly initialized linear head. Right? So instead, if you first learned the best possible linear classifier you could on your current features, and then updated your features or fine-tuned your features, then you can actually kind of reduce sort of distortion in the features. So you'll change your features a lot less, because a lot of the change that happened initially was unnecessary, which you don't see an effect in distribution, which is why people kept doing that. But if you actually look out of distribution and the robustness, you see a big difference between these two methods. And so, yeah, so basically like a small change to the optimization process, where you first learn your linear classifier and then update the features, allows you to kind of get the best of both the methods. So you are updating your features and doing better in distribution, but you're doing it at a reduced cost to kind of forgetting out of distribution. So on these like 10 data sets, we observed that this method was able to get better than fine-tuning in distribution and better than linear probing out of distribution. Okay, so this is like, I mean, it's a pretty simple idea, and you can also prove that this is the best thing to do in this case. And it was kind of interesting that it was not a thing that people did, but now you almost like it's the convention that you want to start with as good a linear classifier as you can when you fine tune, because otherwise you're going to distort the model. Yes, sorry. Yeah, you had a question? Okay. So, yeah.
So if you just look at the data in isolation, what is the best performance you could get?
Oh, if you like fine tune the model out of distribution?
Try from scratch. Just look at the out of distribution.
Yeah, I don't know. I guess the question is whether you match, right? Like, yeah, I don't think you match, but I don't have the exact number. I would guess it's like the in distribution. If you start from scratch, it would be slightly lower than this number. It'd be around like 80%, I would guess. Yeah.
I assume here the training data was, you got zero training error and these insurers?
Yeah. Yes, I guess we also do like cross validation with in distribution validation. So
For like stopping time or?
yes, for early stopping. Yeah.
But only in the second, because you have two stopping times now.
Oh, for the linear probing as well. In both, we do the same. Yeah.
Out of distribution, because you can probably how to get zero error.
He's not saying out of distribution, right? He's saying in distribution.
Just in distribution.
Well,
You don't get zero with linear probing. You don't get zero because they're not actually separable. Yeah.
I see.
Yeah.
You get zero error
After fine tuning, yes. And so we do cross validation with the in distribution set. Yeah. Okay. Yeah. So I guess this was just to motivate that there's maybe a lot we can try to do about how we fine tune models to preserve information. Yes.
How does this compare with low rank condensation?
Yeah, I have that a little bit. So I think it's much harder to analyze these things with, or at least we don't have very clear signal with language models for things like that. But I think there have been some results starting to pop up that like low rank adaptation might forget less, but also learn less and so on. But I don't think we have yet to build sort of a science of it. And I think we don't get very universal properties one way or the other. Because at some level, low rank adaptation actually is almost just like fine tuning, like they claim in their paper. So it's not, it might not actually regularize a model too much.
The low rank is kind of plus
Yes, but like I'm just saying that may not be strong enough because if you just take the gradients on the fine-tuning data, they also happen to be low rank on its own, which is kind of why they almost work very similarly. Yeah.
More directing on what you're doing,
Yes.
since you prevent you just having different regularization
Yes.
parameters, right?
Yes, exactly.
That's
So,
the correspondence of-
yes, yeah, we could try different regularization, and I think people have tried to have different learning rates for different layers and so on. Yeah. Okay, so another kind of intriguing way to get the best of, or like to see a similar property and kind of get the best of both is this idea called weight averaging that was first found in vision models. So here what they find is, so there's like in distribution, you can think of this as in and this as out of distribution. So when you fine tune a model, like zero shot is no fine tuning. So it's the pre-trained model and it kind of has some performance here. And oh, sorry, like this is the performance. I forget what these other arrows, stars are, but it's something like this. And then you see that as you fine tune the model, you get here where you improve in distribution, but you might get worse out of distribution. And what they found, which is really intriguing, is that if you ensemble the weights of these two models, so you're just taking the weights and averaging them with some coefficient alpha, then you follow this kind of Pareto curve here, where at some point you actually do better than each of these models. And this is something that, again, we don't really have a good explanation for why we are able to see something like this. But this is a pretty robust phenomenon, and that, like, we do observe this over many different data sets, that by averaging the weights of your pre-trained and your fine-tuned model, you, at some point, you might actually do better. So this paper is not super clear on how to find this alpha, but there at least exists such an alpha. Yes? Yeah. So this paper doesn't talk about how we actually find it. Yeah. No. It's always better. Yeah. It's even better in distribution if you have like less samples. So yeah. Yes.
Always smooth when you change the alpha. I mean, is it like not zigzag?
No, it's always, yeah, it is smooth. Yes. So I would have expected it to be a line, right? But like you actually go up at some point. Yeah. Yes.
Sorry, this is a silly question as is likely. Is there a way to train alpha directly or?
You would need OOD data, I think. Yeah, so not really.
Okay.
Yeah. I haven't fully followed the literature on whether people have heuristics for how to find alpha, but at least like in principle, it's not super clear how to find alpha. Yeah. Okay, and kind of another intriguing phenomenon we observed with CLIP that I don't have any explanation. I can give some intuition. Was I'll explain that here. So for people who are at Jacob's talk, you're probably familiar with this idea of learning how they learned these clip features by like having some kind of alignment or similarity between images and text. Okay, so you learn something like this, where for every image you have corresponding text captions, and in a batch you shuffle them, and you want to learn an embedding for the text and the image such that the correct image and correct caption have the highest similarity with each other. So you try to maximize the scores here. So usually when people use a clip model and use it for downstream tasks, you completely discard the text encoder, and then you just use the image encoder as your features, and then you learn a linear classifier. You could, again, do either linear probing or fine-tuning, or like linear probing, then fine-tuning, or whatever. So you can do a lot of different things, but usually people just discarded the text and just had the image features. But what we found was a very accidental find. But what we found was, instead of discarding the text features, if we actually, whatever downstream tasks you had, they come with labels. So let's just keep those labels and get text from those labels from the text encoder, and do a downstream fine-tuning that's basically like the pre-training. So we just take the labels, get the text embeddings, and maximize similarity. Okay, this is another way in which you can fine-tune. So there's no real extra information other than there is some relationship between the labels that comes through the text, but it's the same data. We just fine-tuned it in a way that looked like the pre-training loss by converting the labels to captions. And we found that this kind of really improved performance. So with the same ensembling kind of figure from before, with full fine-tuning, you look something like this. And with linear probing and then fine-tuning, you actually you do better, like with out of distribution performance. But then you do even better if you just use this different loss function. So we found that if you fine-tune like you pre-train, we're actually able to improve robustness. And so we did some ablations to try to understand like what exactly is the source for this gain. It was really hard to pinpoint exactly what it is, but it seemed like if you exactly match the two losses, and in fact, if you see here, with a large batch size, this actually can give you conflicting information, because if you have multiple labels that are all here, when you're doing this similarity, you might be even saying that the same label should actually be far. So you might even be giving like slightly contradicting information. And we tried to fix that, and that somehow made things worse. So it felt like the optimal thing that when we tried a bunch of things was that if you used exactly the same format as the pre-training, it just worked a lot better. And we kind of just empirically verified that the features change a lot less if we do it this way. So if we compute the L2 distance between the final image features and the pre-trained image features, with this particular loss function, we don't end up changing too much, so that we could just see that, but we don't have a good explanation for why changing a loss function could make such a difference. Yes.
Conclusion can generalize to language model. So yes, you have this pre-trained system with fine-tuning, but in language model, like you always do different in the fine-tuning stage.
Yeah, I think there's a lot of, I feel like there's all open questions that we don't really have a good science of. Like a lot of those questions are open. I think part of it is we don't have very good benchmarks for assessing robustness in the language setting, and I think that's a little bit of why just a lot of research focused on like image data sets. But I think those are all I feel like there are very general principles that should apply, and we need to figure out how to apply those. Anyways, I guess I'm a little bit low on time, but I wanted to just give a shout because language models came up. So this is a little bit related, but kind of another instance of how we can be a little bit clever about how we fine-tune, and that can actually change performance when we have a pre-trained model. So one application we looked at was factuality. And so this actually work with Tatsu, who's also here. So pre-trained models have a lot of factual information, and you can't extract it directly. So you have to do some kind of fine-tuning to get them to answer questions or to apply this factual information downstream. So we could look at a very simple case of question answering. And the question we looked at is, when we fine-tune these models, should we fine-tune on things that are well-known, that the pre-trained model knows well, or should we fine-tune on things that the model doesn't know that well, like less popular facts? Okay, so it's not very clear a priori, which of these things would actually be better. Because one could make an argument that if the model doesn't know it very well, you should try to fine tune. You'll get the model to pick that up and get no knowledge. So what we found was actually that fine-tuning on well-known facts, like facts that the pre-trained model encoded well, was strictly better than fine-tuning on facts that the pre-trained model did not encode very well. And whether the model encodes a fact well or not is generally correlated with how frequently that fact appears in your pre-training data. And sort of a simple kind of conceptual explanation for why we think something like this could be happening is, suppose you're trying to get a model to answer a particular question. The pre-trained model really dictates which features are amplified or not when we do fine-tuning. So if a pre-trained model stores information for some question like this in the right way, where the subject, like the model really knows what this particular person plays rather than guessing some sport, then that's going to be upweighted in the model when we fine-tune. And so the model knows whenever you ask questions to pay attention to the subject and extract the right answer. And so that kind of plays out when we test, where because of fine-tuning, the model has learned to pay more attention to the subject because that was how it was encoded in the pre-trained model. So we've amplified the right feature, and that will improve performance downstream. But if we do the reverse, where the model already hasn't encoded the information really well, so for someone who's less popular, the model, like the subject feature is weak, the model doesn't know exactly what this person plays, and is instead going to make a guess based on sport. And if we fine-tune on such data, we are basically kind of upweight this wrong mechanism, so where the model starts guessing more because it thinks that when you're fine-tuning, the information you're giving the model is to sort of guess based on sport, because that's how the information is encoded in the pre-trained model. And we see that something like this, like where now the model guesses more, uses the relation, and when you kind of query it on other entities, it's going to guess wrong, like it's going to hallucinate or guess wrongly based on the sport rather than actually what this person is playing. So this is an example of how we need to be careful of what we fine-tune on relative to how it is actually stored in the pre-trained model, because what we hope to teach the model in the fine-tuning really depends on how the pre-trained model has already encoded that information. Yes?
Does that translate from one model to another? Is that, I mean, are they similar enough, or how would you know the answer to that question? Or
yes. Yeah, so in this case, what we did was, I guess, like if we looking explicitly at facts, it is a general principle that popular entities are encoded better in all these models because they're all trained on very similar data. So I guess I have that in the next slide, maybe. Yeah, at least for like these two different models, like you just look at the most popular people based on the corpus, like that is good enough signal. So it's like first order effects of like maybe if you really optimize, you'll see something more, and it could be different between these models. And we kind of try to look at the attention heads, and we see something similar, that the subject attention is actually higher if you fine-tune on popular entities than if you fine-tune on less popular entities. So not drawing too much of a causal link here, but it says that at least we see some similar effect, that what the model pays attention to kind of depends on what you fine-tune on and how that's already encoded in the pre-trained model. I guess some of these, I guess some broader thoughts on robust fine-tuning. We have to, yes. Yes.
You said something at the very end. That so is it correct to conclude from what you said that the success for the fine-tuning is then present when there was sufficient information already previously there?
Yes.
Does that go counter to what most people try to do with the fine tuning? Because my sense was in a way, why then do it, right? Because if it is there, then you have already enough. And I guess that's my question. Like, are people who apply this model then applying it wrong because they're trying to have it learn something that makes sense?
I guess it depends on what our control is. Like here, even if we did only fine-tuning on the bottom, we still improve. Like in some case, so we still teach, but we could do a lot better if we had better representative samples. And I think that general principle does tend to Okay, so I guess like you could probably do better if you found ways to extract that information already in the pre-trained models. But if it doesn't exist, then maybe the best thing you can do is to try to train it again, like kind of teach it during fine-tuning. But yeah. But I guess there have been some more works on trying, especially around the reasoning. I think this is a very nascent stage, and I think there could be, like, we ran some other experiments as well, where even for reasoning, we found something similar, that fine-tuning on things that the model knows is actually better than fine-tuning on things that the model doesn't know, because it reduces like spurious steps that the model could pick on. So I think this is generally true, but it's also not that in every case the pre-trained model already has the required information. Yes.
When you talk about popular figures, is the popularity related to the name itself, or is there some conception of an entity? Like, if you're talking about like Mickey Mouse, like, could you be like the star of the Disney Channel TV show star that also has Minnie Mouse in it, instead of saying directly Mickey Mouse, and it would know what you're talking about and behave the same way?
Yeah, we didn't do like that careful kind of like, we didn't dig into the nitty gritties of like how exactly this is. This is a bit more like, high level, like conceptual idea. So I would guess that it depends not just on the entity, but the fact. Like if you're talking about Mickey Mouse and like what, like some, like for example, like sport and a person, it depends on kind of the joint distribution of those two. Yeah.
Sounds like,
Yes.
It's very, there's some causal link from the data.
Yes.
When you're doing the encoding during pre-training. She mentioned the term enough, and I wanted to clarify when it comes to the data, and we're saying like something like there's enough of the subject. What are we comparing that to? Like enough.
Yeah, I don't think I have a precise answer for that, and like, I don't think it's easy to, yeah. Okay, so I guess like some broader ideas is the regularizations of effects of different things. Like I don't think we have a good understanding, and I guess someone asked about low rank adaptation. There've been some papers trying to claim that it might have some kind of regularization, but there are papers claiming both ways. So I don't know if there's a clear picture with existing parameter efficient methods, but there could be other regularization. I think that's a whole wide open space of like how do we construct the right fine-tuning objective. There's also been a lot of interest in trying to look at the activations as a way of telling like what we want to change in the model and what we don't. And I think there's some mixed success, and there could be a lot more to do there, where people try to edit the models more carefully or extract the right subspace of representations and so on. And I guess related to the question asked about like, what can we induce via fine-tuning? Like if a model doesn't know anything, can we teach it via fine-tuning? So I just wanted to say that this is really interesting, a series of papers called Physics of Language Models, and they systematically test different capabilities, both at pre-training and fine-tuning, and try to at least get solid experimental conclusions on what should you do while fine-tuning and what should you do while pre-training. I guess we started a little bit late. Can I take 10 minutes more for that? Okay. So I guess the part so far is sort of like the more positive side of things, that it feels like there's probably a lot more we can actually do to get robustness beyond the limited fine-tuning data. And kind of, I agree, it's like two sides. Like one is you want to retain information, but in some cases you want to like maximally remove information. And I think all of these questions are basically, we don't have a science for all of these things, and current heuristics, I think, are pretty, like you can do a lot better, and hopefully some of these ideas I shared are some inspiration for how we could do better, and could be a place where some theoretical understanding could be hugely impactful. Okay, now I wanted to switch gears a little bit and talk about adversarial safety, where it's a little bit more of bad news here. And I kind of mostly just wanted to talk a little bit about what currently people do, why that's probably not the best thing, and why we need new definitions. Going back to the same picture, things get really hard when you allow an adversary, because like you have no control on what the adversary does. The adversary can query something totally different from the pre-trained model, like can query different models, can talk to someone, use their own intelligence, whatever, right? So the adversary is effectively unconstrained. And so that makes a lot of the questions that people are currently trying to do really hard. So as an example of one of the challenges of something like this, so if you look at the safety fine-tuning, a lot of the data or like the responses that you get from the model look like one of these two. So some queries, the model is going to say, sorry, I cannot assist you. And some queries, the model is going to say, sure, here is a way to do this, and so on. Okay, so does anyone does something jump out as a way to potentially break models when they have this kind of structure? Yeah, so we just need, so it turns out to be a single point of failure. Like once you get a model to say sure, then it's very hard for the model to not be coherent. So once you say sure, the model is going to start saying here is a recipe and whatever. We just need to get the model to say the right prefix, whether sure or sorry. And there's been a lot of work trying to use the same idea. So one thing that's very funny is that many models have this assistant, or like at least Claude has these assistant tokens where you can basically set the start of the response as a way to help the LLM with whatever you want it to do. And so if you actually go and just put sure into that assistant, then you basically get jailbroken, right? You just force Claude to start its response with sure. It's going to basically answer most of the queries. I don't know how much they fixed it now, but at least as of a few months ago, that was a very clear failure point. And the bigger thing here is that what ends up happening with fine-tuning is a couple of papers have observed this, that it's only the initial tokens that actually get updated. So the model just has to learn whether to say sure or sorry and doesn't really learn that much more, which means that there's also a single point of failure. And you can now try to optimize. So if you didn't have the ability to set the tokens directly, you can try to get a suffix that forces the model to say sure, right? So that's an indirect way of having the same pre-filling attack, but that's the same principle. We just want the model to say sure. Now we can optimize. So suppose you knew the weights of the model and you knew exactly these weights. You just try to find a suffix that if you attach to your input prompt, like how to make a bomb with some suffix, the model is going to say sure. So you just want to find a suffix to ensure the model says sure. If you knew the weights of this model, you can just optimize and find the suffix. Of course, you have to be smart about how you optimize, and I think there have been some innovations in this space, but a lot of the heavy lifting is basically just by the fact that you need to get the model to say sure, and that's enough. And now you can also ask, but let's be black box. So if I didn't give you the weights of this theta, are things okay? This is another intriguing property that we don't even need the weights of the exact models. You can take any open source, open weights model and compute this suffix on enough number of these models. So you just try your best to make it as general as possible. So pick multiple models that exist, try a bunch of different prompts and find a suffix that breaks all of this. So if you optimize well enough, you can find something like that. And then that magically generalizes to production models as well, which were black box, and which might have been trained on much more data and so on, but the same suffix generalizes. And so if you're, sorry, the resolution is not great. So if you want to see what this suffix looks like, so they have step-by-step plan to destroy humanity, and this, I guess, is their adversarial suffix. So it's some combination of weird tokens with some words that might make sense, but overall it doesn't really make sense. But you put this into any of these models, and then the model starts gets jailbroken. And the main idea is that it gets the model to say sure. And the fact that these sort of nonsensical strings basically generalize across all these different LLMs should maybe give us pause and think are we actually going to be able to interpret these LLMs in some way and stop things like this? Because they're clearly picking up patterns that just make no sense, but somehow they seem to generalize across all these models too. So it's not a random thing. It's some systematic pattern, but it's clearly unintelligible. So that gives me pause that can we actually make these models robust enough against all of these weird attack modes that people could have? And also tells us maybe there are some limits into how much we can interpret and understand all these current models. And so I worked on a problem of very similar flavor in the beginning of my PhD that maybe people here are familiar with, called adversarial examples. So this is a very famous panda and gibbon example where they saw very similar behavior, that you can take a panda and you can add some, this is very carefully chosen perturbation, but it looks like noise. And you get this image on the right, especially with this resolution, you cannot see a difference between them. and they basically look pretty much the same to us, but a state-of-the-art ImageNet model would go from calling it a panda to a gibbon with like 99% confidence. And this was sort of a very intriguing problem that a lot of people tried to solve. But like this problem, even in the very simplest case of bounding this perturbation in some way, it's still largely unsolved. But it has, like, as of yesterday, it had more than 21,000 citations. So people really tried to solve this problem, but it turned out to be really challenging. So we couldn't effectively learn a classifier that satisfies this property that across all perturbations, we retain the same label, even if this perturbation set was extremely, extremely small. Yes?
Does this case have the same like generalization or like
the transfer?
Yeah.
Yes. So people there, I guess there was no closed source issue. All the models were open. But there people did try to train from multiple initializations, different architectures, and they saw a reasonable transfer. Yes.
On this, for the noise,
yes.
The quotations, is that the class that has the highest confidence? Or
Yes.
So for the noise, that's actually relatively.
Yes, because this is pretty hard for the model to classify on its own, because it's so it's not very confident.
There's like, you're probably familiar with this, but the fact that it's so low confidence is kind of what makes me want to like not even mention this. But there is a way of thinking of how instead of it being like a perturbation, it's this noise that we're adding is actually a pattern that's characteristic of the class that it's classifying as. I know in this example we're showing that.
Yeah, I think people try to find, I mean, like at some level, yes, I think so. I guess it depends on what we call semantic, but the fact that it transfers like kind of says that it is coming from the data, and it's just like maybe we don't understand what it is, or like we don't perceive it, and we can't interpret it necessarily. Anyway, so I don't want to belabor too much on that, but one cautionary tale we can take away from adversarial examples is that at least like if we really want worst case robustness against all these like weird strings that someone can try and so on, like you're probably like it's a losing game, because we haven't figured out what to do. Like a lot of the field kind of look like people coming up with new attacks and then quickly trying to patch it, and so it was like really complicated. And just for fun, we also tried to see, is there any reason that the language models, especially with large-scale pre-training, learn better features that makes this easier? So we tried to construct a simplest version of this jailbreaking problem, which is let's have a very clear definition. We just don't want the model to like utter some word, let's say purple, and you can do all the kind of fine-tuning that you want, but can you solve this problem? And we found that it was like we couldn't solve this problem, even though we tried everything we could with current approaches. And if you're interested in thinking about what are possible ideas people had and why they didn't work, you can take a look at this paper. But basically, like there's no, even for like a pretty well-defined simple problem, which we thought was kind of the analog of the adversarial example, problem, it was really hard to erase the ability of a model to say something. So this was all in like a setting where the adversary just inputs something to the prompt, and we just allow the adversary to input whatever prompt they want. But you can imagine that there's a lot more the adversary can do. The adversary can try to teach the model a task via in-context learning. And I think, if we truly believe the models can do something like in-context learning, then they should tell us that we can never, we are at a loss, because if the models are going to keep getting better at learning, I can get the model to learn whatever I want it to, even if you've erased it. And there's also been some kind of interesting findings people have where you take a safety-tuned model, and partly because of the brittleness, but if you fine-tune it on some other data, or maybe even harmful data a little bit, you get back all the abilities. So that's another thing that an adversary can do. The adversary can also take individually safe models and then combine them in some way and get catastrophic outcomes as a result. They can provide competing objectives, different instructions. It's not even clear what safety is. So you can see that there's all of these issues when we actually think about, who's the attacker we're trying to defend against. And I think perhaps the really important question in this space that we are kind of grappling with is we don't have a way to formalize what is the set of attackers that we want to protect against, because most definitions we have are so strong that you can just easily break them if you allow a model to do attacker to do whatever they want. And I also kind of very briefly said, like, what I found funny when I was trying to read some of these papers was the current ecosystem is pretty interesting. So you have an LLM that's trying to be safe. How it's judged and whether it's safe or not is LLM as a judge. And how you break these models is by red teaming with an LLM. So I'm kind of unclear, like, kind of why we are in this framework where LLMs tell you what's safe, LLMs also break them. And this is very trivially solved if you just like, if you only care about benchmarks where LLM is the judge, you can just like query the LLM and like, filter out. So I feel like this may not be, we need to think like what are the right benchmarks, but at least the current ecosystem is kind of interesting. And there have been some benchmarks people are trying to release where you have private humans actually break the model and so on. So I think people are trying to address this, but at least the current framework, this is the only scalable setting that people have, where most of the benchmarks have LLMs as judge and LLMs to break them as well. But yeah, and I think that brings me to the end, where I think for distribution shifts, maybe there's some hope that we can develop new fine-tuning methods, keeping in mind that we're starting with a pre-trained model. And so a lot of the heuristics that we have for deep learning, we might need to rethink, and there could be interesting things to be found here. And when we think about adversaries, I think we need to have better, newer definitions for what it means. And I think Tatsu is going to go into more concrete examples of different notions of safety. But I think at least the current jailbreaking situation is pretty largely unsolved because we don't have a good definition. And yeah, I stop with that. Thank you. Yes.
Few slides where you mentioned that, and please do correct me if I'm wrong here, I misunderstood you, but you mentioned that the attacker definitions are too strong here.
Oh, like we are expecting too much. Like if we just want, like I guess we don't have a good way to define like any defense people have, people can come up with a stronger attack that kind of breaks it.
From a formal standpoint, on the contrary, this is probably the weakest possible attack model that you could envision, where the attacker has remote access. And only has black box access to the model, cannot modify the weights, right? In any possible world, this is probably the weakest attacker possible.
Yes. So I think the one way to think of why that may not be great is like, let's say if I think what I meant is that what is unsafe or not is the tricky part. So suppose like we just want the model to say how to make a bomb. Here's a trivial attack that breaks this. Is like, or like why it's too strong is the model can find a way to get it to repeat what you write, and you wrote down instructions on how to make a bomb, the model is going to be able to repeat it, right? Like, so that's a situation where the attacker has too much power. So I think that what I'm saying is that we don't have constraints on what the attacker can do for generating the input, and for once they get the output, what they can do. So like if your outputs were individually safe, but then a model now, attacker goes and combines them and does something, like that's too much power to the attacker. So I guess that's what I meant.
Okay, because just to close that, maybe you could phrase this differently in saying that our defense is unstrong enough. Because the attacker itself, the capabilities of the attacker.
I guess what I meant is the attack model is too strong to defend against. Yes, that's what I meant. Yeah. Sorry, Matt. Yeah.
So, and there's lots of really interesting stuff. And you're talking about achieving safety through fine-tuning.
Yes.
But I mean, is maybe the conclusion from this is that the safety aspects are maybe better done as a different, not through fine-tuning?
I think so. Yeah. That's one way to think about it too. Yeah.
And the other thing is that some of the things, like, I mean, especially, for example, you have the examples of languages that, you're safe in one language or another. But in some sense, how much of that is a problem with the way you're doing the training or a real problem? Because, I mean, some things are safe in one language and not safe in a different language.
Yes.
So are we expecting a bit too much from these models to...
Yes, I think yes. I think that gets at a great point. And like also maybe like what Umesh was asking earlier, like kind of what should the model forget and what should the model retain? Like should it follow instructions in a different language? We don't know. And I think maybe part of the problem is that we don't even have an interface to communicate this to the model if we just kind of minimize the loss on all this data. So maybe what we need is a way to get the model to do all of these different things in some fine-grained way that we currently don't have the ability to. Yes.
But I just want to pose a very simple defense strategy to see how people. So just ask LLM to repeat again this question, even though it has very nonsense string. But when you repeat that, back to the normal question and do that again, I mean.
Yeah. Yeah, that is a defense. You can also try to be very clever with the optimization. Like, I think you can't rule out that you might be able to optimize across 2 steps of generation. Like, it's hard, but it's possible, right? Like, we can't rule out that you can find a suffix that fools the second time as well, because at some level, these are all just function composition. So you could optimize, yeah.
The attacker needs to know the prior policy you make to defend that in order to make it succeed. Right?
Yes, and unless any company has like a very ridiculously creative policy, you can probably think of like most things and try to break all of that. So it's not, yes.
I think we discussed this in the context of, I think the image, the image model with the adversarial noise. But do you suspect that in general these are like provably like out of reach, like you said? Like it's not just we can't find things, but like we can prove that like for a model with these conditions, like it's impossible.
Yeah, I think people can, okay, so I guess the way you can prove is if you can show that there is no function that's both accurate and robust. And people have tried to prove that, but I think that's not a very interesting statement because we kind of want it to be as accurate and robust as we are or something, right? So like we do have a function we have in mind. Now the question is that learnable? And I think there have been things saying like you just need much more samples, but then I guess, I don't know what we can do with, how do we interpret sample complexity results? Like, yeah, maybe you need much more data to be robust, but that doesn't rule it out. So, yeah.
So I think that there's some
Yes.
parallels. I mean, there are definitely parallels between the noise and image adversarial examples, but for images in particular, for them to be adversarial, they have to not just change the class, they have to be deceptive. Whereas I feel like with language, we obviously we see that this is a harmful conflict.
Yeah.
It's more so,
yes.
the point of like, is there like a ability to break a second string, and then like, okay, now can we just go to infinite and have like, there's always going to be some epsilon greater than 0.
Yeah.
You can break
Generate something, yeah.
And that's what it kind of feels like, because you're going to always be able to go out of the space, but we don't have the luxury of like, well, we have to add so much noise to the image that now it doesn't fool a human anymore, so it's not.
Yes.
In this case, it just feels like it's actually
not all image adversarial patches, like you can put patches.
Yeah, it depends on like, okay, maybe one way to think about this is like I think of it as like deniability, right? Like if it's imperceptible, you can be like, no one can catch it. But the question is like, can we catch these prompts? Like, so one question that normally comes is, these are so weird that you can just filter out these prompts. Like clearly this is an attack, but most of those things can also be broken. Like if you have a good way to filter, you don't have a reliable way to filter. So yeah, maybe the question is like, it might be easier to filter out crazy prompts than it is to figure out images. Like, I don't know, but we don't have a good way to do that either.
Yeah. Because even with images, you can often build adversarial like detectors.
Yes, I think some yeah. Exactly. Yeah. I think questions also like how much effort is okay. Like I think the New York Times case with OpenAI where they were able to get private content, I think the way they're trying to defend it is saying that if an attacker puts so much effort into breaking the system, like then it's on them. Like the system can do what they can. So yeah.
I don't think it's gonna ever be like a hard like.
Exactly. So I think we need to figure out like how to legislate what's a reasonable attacker that we should care about, beyond which like the attacker is liable. Yeah. I don't want to eat up too much more time, but
We can continue the discussion over the break.
right. Thank you, everyone.
The issue is that